Hello, everybody.
Hello.
Good to see your forehead. Hey, Calvin, how's it going, buddy? Hi, Kenya. I'd like to be under the sea in an octopus's garden. Something like that. Isn't that nice? And Aditya, how are you doing?
Not too bad. How about yourself?
I'm all right. I'm all right. I'm all right. Ikun, Ivy, Kai. Excelente. So, hello, Carla. I have my computer set up differently today, so I see everybody's faces like you come up, it's like boom, you're there. And I'm probably more there today too because I'm not sharing a screen yet, am I? So what I'm thinking about is I decided sort of at the last minute to talk about something wild, wacky, weird, and wonderful today, and it's not cuttlefish. Although we will take a short segue into cuttlefish world. But we're going to talk about moss bower spectroscopy. But I wanted to finish up the chat on the finish up the chat on the Greubele paper first. So let me grab that guy. I've been kind of scrambling to get ready, obviously. So protein folding dynamics questions. There we go. And let's see, where did we get to here? I've got to find the Greubele peanuts. There we go. There we go. Okay. So, David is not part of our class. How did these get in there? Okay. So we kind of finished up with the idea of uniform repeating and how that's actually a little bit tricky, and you need a small alpha value for the material, a small material absorption coefficient, and a fairly intense beam so that you still get a lot of photons absorbed, but you don't get a whole lot more at the front than the back. And so we talked about that last time, so that's not a huge deal. And we talked about why you make a 2 millimeter hotspot with the YAG laser, and then you sample, and then you excite with a UV beam of 200 microns. Now let's talk real briefly about what the UV beam diameter was. This is the YAG description here, and for the excitation they used a titanium sapphire laser, and so sapphire is aluminum oxide, and you can dope Al2O3 with TiO4, and the titanium, it's probably substitutionally doped. So the titanium has an extra electron or something, and it forms a chromophore. And so, and Ti sapphires they have a very broad emission wavelength. So you can tune their cavity to excite only a narrow range of wavelengths into a laser. And so they are exciting around 280 nanometers plus or minus 7 nanometers, right? This is the bandwidth is 280 plus or minus 7, so it's probably 277 to 283 or so, right? And the pulses are 2 milliwatts. Right? And they don't say how intense the pulses are, but they're probably what they probably have to do is they have to tune the pulse intensity so that it doesn't bleach the samples. How's my audio? Am I okay? Excellent, good. Just let me know when it goes to shit, and I'll do the toggling thing. So so getting the excitation pulse strength to a suitable level is an experimental thing, and you might use neutral density filter or a beam splitter or something, and, to sort of filter out some of the beam. But so you excite a 200 micron diameter spot instead of a 2 millimeter spot. So it's basically 10% of the area in a small circle in the middle of the hot spot. So that assures that thing is heated uniformly. So if you're the sample, then you get boom, boom. You get these two heating pulses separated by a few nanoseconds, right? Then you're going to get a they don't mention the pulse time on the Ti sapphire here, but I'm sure it's sub-nanosecond. So you get pulse for the heating pulses, then suddenly the water there is hot, right? And all the protein is out of equilibrium. And then this Ti sapphire pulse that's tripled with these BBO crystals. I forget what BBO is. There's a number of non-centrosymmetric crystals that can frequency multiply light. So they have a nonlinear refractive index, so that as the intensity gets large, they produce harmonics of the fundamental. And that's about all I know about it. It's actually fairly deep water, but the use of frequency doubling is actually fairly common now. For example, you guys have all seen the green lasers, right? And laser pointers. Those are frequency doubled YAGs. There's a little YAG laser in them, yttrium aluminum garnet, that emits at 1064, and that is put through a frequency doubler to half the wavelength, right, which is 532, and 532 is green. So the green laser point uses a frequency doubling crystal in it. Now, one thing that happens with those lasers, however, you have to be careful if you ever play around with them, is that especially the cheap ones do not filter out the YAG. So if you get an intense green laser, it's actually probably 4 or 5 times more intense than it appears to the eye if you add in the 1064 radiation. So be careful, right? It can get really hot and thermally as well as optically hot, you know? So anyhow, the Thai sapphire beam is tripled. And I think it's around, well, we can multiply 280 times 3. We get 600 plus 8 times 3 is 240. That's 840 nanometers. So there's some 840 nanometer source, or the Thai sapphire is set to 840, actually. That's a setting that you can use for Thai sapphire, and then triple it to 280. And that guy is set down to 200 microns, so it's in a uniformly warm part of the solution. And then the fluorescence is imaged onto a 600 picosecond rise time photomultiplier tube and a 2 gigasample per second digitizer. So 2 gigasamples is 2 billion samples per second. So it's taking a sample every roughly 500 picoseconds. And it can store 1 million samples. So that's pretty good. I'm sure we can do better nowadays, but that was probably pretty expensive stuff at the time. So that's the optics there. And question we're working on is, damn. So we sort of skipped over that. But that's the wavelength of the UV, the wavelength and diameter of the UV, etc. Now we go on to these so-called steady state measurements. Okay? And steady state is a slimy description. Okay, but let's look at, I'm not really being super critical of the paper, but let's look at these words and see what I mean by slimy. The steady state has a particular meaning. Steady state is like if you have a big lake draining into a little lake or something, or draining into the ocean, right? And the river is flowing at a steady rate, right? That doesn't mean that it will flow that way forever. It just means that for the time being, it's relatively constant, right? It also doesn't mean that there's anything at equilibrium, right? Equilibrium would mean that the water wasn't flowing at all. There was no net flow, right? So steady state is like there's chemical reactions which happen, some steps are in steady state, right? Usually they're not rate limiting steps. No, I take it back. I don't know about the rate limiting part, but there can be, in the bromination of acetone, for example, there's a steady state transformation of, I guess, the enol form of acetone into bromoacetone. And so that one is independent of other things. It just proceeds at a more or less constant rate independent of all these other concentrations until stuff runs out. And so steady state does not mean equilibrium, but it does mean that a steady change is happening. Now, what they're talking about here is this foundational figure here, which describes the expected folding state of the protein after a few seconds. And there's from the cold denatured state here at the lower end at minus 6 degrees C, and then going up to positive 20 degrees, there's a substantial change in the ellipticity, right? It drops down and kind of comes back up. And then it increases as the temperature goes up, and then it denatures permanently. This area up here is permanently denatured. Right? Then if this is cooled down to 20, then the ellipticity is here. So the idea is that these states are neither equilibrium nor are they steady state, but they're reliable. But to the extent that this paper is valid, these are reliable states of the protein, folding states of the protein at these different temperatures, both in the native conformation or in the temperature range where the protein doesn't permanently denature. It undergoes this partial cold denaturation, which can be reversed, right? So by drawing a line from this upper dashed line to the lower dashed line, we can change ellipticity into folding state. And this is speculative at best, I guess. But this is an important part of the paper, right? So at 20 degrees, if the ellipticity is minus 13, we would say denatured. And if the ellipticity was minus 18, you would say native. Right? And then at minus 6 degrees, if the ellipticity were up here at minus 13, hi, Kaysa, how are you? You want to say hi to my students? Say hi. This is Kaysa Wolke. This is Ivy, Richard, Hikun, Kai, and Aditya. That's Professor Wolkett's daughter. So so it's, I don't know, it's all a bit much, right? But you can see here that if we follow this line here, when we plot its relative distance between these two dashed lines, then it sort of transforms into this. And the only part of this that we're really concerned about is between about 20 degrees and minus 6, because we don't temperature jump outside of this range very much, right? So if we start at minus 6 and we're sort of at a, say, 30% folded fraction, when we jump the temperature to 20 degrees, we make an instantaneous jump here, then we can follow the folding fraction go up to nearly 100%, as basically this ellipticity fraction drops down here. So now Carla, bless her heart, is always making a mistake when she interprets this. And that mistake is what, Carla? Where's Carla?
Is it because I keep saying circular dichroism? Is on.
Did anybody hear that? I didn't quite hear it.
Yeah, she said, is it because she keeps saying circular dichroism?
Right, right. Circular dichroism makes these not really equilibrium, not really steady state, but these time independent measurements. These I'm not changing, I'm sort of at equilibrium with the temperature measurements. And let me just ask a sort of a weird question about how they get this open square data point here. So this is on the thermally denatured protein at 20 degrees. And down here, this is the native protein structure at 20 degrees. And how do they get this protein specimen to give us this ellipticity, or how do they arrive at this unfolded or denatured structure there?
I mean, doesn't it say in the figure that they held the sample at like 70 to 95 Celsius for an hour and then cooled it and then took the CD?
Exactly. So now, why is this guy here different from this guy here? Calvin. Why is this denatured state here different from this native state here? Or what is the difference between these two? It's the same protein, but it has a different history, right? Did I make that? I think I made that. I think I unintentionally made that hard question to answer. But
Wait, isn't it because they heated it up and then they cooled it down and that's why it's denatured, because it was denatured at one point, or they cooled it down to 20 degrees.
Right. So they heated it up to like 95 degrees C. They almost boiled it. And then they cooled it down. And when they cooled it back down, it didn't refold. It just collapsed into a new random state there. And so that's why this guy is up here, and then the folded state has a different ellipticity value here. Remember, ellipticity, it's just sort of it's a metric that's sensitive to the amount of beta sheet and alpha helix. You know? So it's not really it's the best we have, you know. You can't get a protein structure on a dilute protein in aqueous solution. You know, but you can get a CD spectrum. You can estimate the amount of alpha helix and beta sheet from that CD spectrum. And if you want to, you can reduce that entire CD spectrum into an ellipticity value, into one-dimensional parameter. And that's what Greubele did here. So, how do I give someone the mouse? How do I give somebody the mouse? I would like to give the mouse to Dan. Or Adam, do you want to take the mouse?
As a pre-warning, anyone that you use the mouse to, your settings change. Everything moves to the top for some reason.
No worries, I'll take the mouse.
Okay, how do I give it to you, or how do you take it?
That's something that well, you click the mouse give button.
The mouse give button. Mouse give. Okay, so it's probably,
And if you go to the top, and there should be a thing that says view options, and you can request remote control.
remote control.
Right.
Daniel, and I say approve. And now Daniel has the mask. Great.
Do I have control now?
Go down to the lower of the two, figure 2B down there at the bottom.
Yes, this one.
Exactly. Exactly. Now I want you to trace out the trajectory of the temperature jump.
The trajectory of the temperature drop? Oh, I see. Yeesh. Well, I've got two lines here. I guess it would be
Yeah, it's somewhere in there.
or folded fraction is the native. So it's going to go up here and then back down there.
No. Very good mistake. Thank you. Thank you. Who can tell me what Dan did wrong here? I mean, what I'm doing is what I'm trying to do is trace out the kinetic experiment that was done with the temperature jump. So the temperature jump, we start at -6 degrees and about 0.3 folded fraction, right? And we start right at about there, right? Then, boom, boom. In 10 nanoseconds, now the sample is 20 degrees C, right? So what is the ellipticity now, or is the folded fraction now, has it gone up to 1 instantly?
Basically.
No. No, it hasn't. Right? Because in those 10 nanoseconds,
Oh,
water, right, but the protein hasn't caught up yet. So on this diagram, where do we move from that -6.3 in the instant that we heat it?
the instant that we heat it doesn't move, right?
Well, the temperature changes, right? So we go from -6 to +20. Right. So we're out of equilibrium. Right? Right, Dan?
Oh, yeah, sorry.
Yeah, because we've just instantly heated it and we have not given the protein time to equilibrate to that new temperature, or to accommodate that new temperature, right? So then over the next 200 microseconds, what happens to the foldedness of the protein? It folds right, exactly, it goes up. So it instantly translates over to 20, and then over 200 microseconds, it goes up to close to 1. Right? And, okay, great. I'm going to take it back now. So, now, watch.
Oh, I have control of your mute. That's
Oh, I love it. I'm muted. You guys must be happy. So, can you guys hear me still? Okay, good. So now what's happening is that we're in that no man's land, and then we start giving these excitations. Boom, 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 boom. Every nanoseconds, or every 10 nanoseconds, right? We give it a new excitation pulse. And we do this for 1,000, 10,000, let's see here. Every nanosecond. And we take these guys at on a 500 picosecond time scale, right? So this is 100 measurements here. Wait, no, this is 20 samples between 1 nanosecond and 10 nanoseconds, roughly, right? So 20 samples here. And then 20 here, and 20, 20, 20, 20, 20, 20, 20, until we get down to 200 microseconds. So 200 microseconds, let's see here. 200 microseconds divided by 0.5 nanoseconds. That is equal to 200 times 10 to the minus 6 over 5 times 10 to the minus 10, right? So this is 2/5 is 0.4 times 10 to the minus 6 over minus 10. Wait, no, it's not 0.4, it's 40 times 10 to the 4, which is 400,000 data points. So in this 200 microseconds, they take 400,000 data points. And each 10 nanosecond time frame is plotted, and they derive kinetic information from each of those 10 nanosecond pulses. So, so it's basically, you hit it with the heating pulse, and then you just you just keep hitting it with this ultraviolet pulse, right? You just keep monitoring that tryptophan. What's your state? What's your state? What's your state? What's your state? You know what I mean? You keep cycling photons in and out of it, right? You totally, and this is why they probably don't give the intensity information for the titanium sapphire excitation laser, because it's probably not easily known. You know, they have to. I know that they use an internal standard. Sometimes they use this this molecule in there that has some known fluorescence, quantum yield, etc. And so they can sort of standardize the intensity of their fluorescence, but they have to do all this ultraviolet radiation without heating the sample at all, right? It's got to go from -6 to +20 and stay at +20. Hopefully it's not at +30 by the time they're done here, right? Because that would not work. Right? So they hit it with the heating pulse, and it's out of equilibrium, and then over the course of the next 200 microseconds, they take maybe 100,000 or maybe 10,000 or so transients here. And those transients have to be what's the word? Not intense, but they have to be light enough, like not intense enough. Or they have to have a low enough intensity that they don't damage the sample, they don't heat the sample, they don't do any UV photochemistry. And you just have to get that little bit of fluorescence to come out, right? So what we see here is this time. This is probably 1, 2, 3, 4 this is about 2 nanoseconds, right? For 2 nanoseconds, the intensity is increasing. So probably what's happening is that the light is on these 2 nanoseconds. The Ti-sapphire irradiation is on for these 2 nanoseconds. And then for the next 13 nanoseconds, the excitation beam is off, and we just observe the decay over that time, right? So this decay here gets fit, oops, make you guys smaller here. It gets fit to this type of curve, right? Where, here. So the fluorescence decay, the lifetime of that, that long component, I think, is plotted here. And then at the time of the heating pulse, it jumps up very quickly and then it slowly reaches equilibrium. And then it's this slow approach to equilibrium that in which all of the kinetic information from this paper comes. Does that make sense? Somebody tell me what I just said so I know that I'm not just talking into a vacuum.
Dr. Terrell, things are kind of making sense up until graph F for me at least. Why?
Yeah, kind of on the same page.
This Chi2 one?
Right.
Mm-hmm. Yeah.
Especially on the right-hand side from 30 to 400, and I don't understand what, yeah, not sure what's going on there.
Yeah, so excellent point, right? So what's happening is that each of these transients is being numerically fit to two time constants, a fast and a slow time constant. And the slow time constant, Chi2, is I guess it's around 7 nanoseconds or 7 microseconds, right? And so this fraction of the decay time at the time of the heating pulse jumps up pretty quickly and then slowly converges on its final value over the course of the next several hundred microseconds. And so this last area here is just exploded between 0.9 and 1 here. So there's a little bit of noise, right, from oscillation. It's not really evident on this scale, but it's a little more evident on the banded scale to the left.
Okay, that makes a lot more sense.
Yeah, I'm not exactly clear about how, like, it seems like a lot of the information, there's this very fast step here, and then there's a much slower step here. And I have forgotten exactly, oh yeah, I see. The Chi2 parameter is equal to A2 over A1 plus A2. These are the amplitudes. So it's like the fraction of the total amplitude that is in A2. Oops, is here. So before the well, it's cold denatured, it's got 0% A2, then after it's thermally renatured, then it approaches that final state with two steps, a fast step and a slow step. And we can look at the transients here. It's a total of about 12 nanoseconds, right? And there's two components, F1 and F2, right? And these two components are, oh gosh, oops, sorry. Anyway, the two components are different, right? And there's temporal and amplitude differences. But what they're emphasizing in this part of the paper is the amplitude differences between those two components and how it switches mainly from all A2, or instead of all A1 here, all A2 here. And so yeah, that's basically what this is saying. So there's subtle differences in the temporal structure of the fluorescence recoveries as time progresses between the first nanoseconds and out to a couple hundred microseconds. That's really all. That's really all that I care about. Right? There's more. The actual fitting is a bit of a mess. Whenever you fit exponentials, so there's basically I'm going to try. Hold on. I'm not sure if I'm going to be able to get this in here or not. Are you fighting me, Dan? Yeah. Man, I want to turn my camera on. There we go. We need this. It's this icon at the bottom here. Ah, that's capture ways. Don't go there. Okay, hold on. So, come on, you.
I'm controlling you. What am I doing here?
I don't know what you're doing, man.
I mean, what's the goal here?
Don't let me do it.
I mean, I've got to be able to turn this off, right?
Yeah, possibly. I don't know.
How did I get control again? I thought. Okay. It's a blank thing here.
So the thing that's going to be up here on remote control, board control. There we go. Now I got it back.
Nice.
So for some reason, it's coming up dark. Come on. There we go. So this is about 50 billion miles away now, but I'm going to talk about the fitting of exponentials. Right? It's a mess and it's a stretch. You have 4 parameters out of like 20 data points, right? They have these data sets that kind of look like this, right? The whole thing is about 15 nanoseconds. All right, and what they have to do is that they're fitting this part to the following function. It's A is equal to, well, A total is equal to A1 times E minus T over tau 1 plus A2 times E minus T over tau 2. Right? And so there's basically 4 floating parameters. There's A1, tau 1, A2, and tau 2. And it's actually much easier to fit A1 and A2 if you pin down tau 1 and tau 2. And I think that's probably what they did. They fit a whole bunch of them. And they said, okay, this tau 1 and tau 2 combination are suitable for all this fitting. And they tried to collapse most of the informational part to A1 and A2. Does that make sense, Ivy? Yeah. So, you know, you can take, like, for example, if you take the, and, you know, when you have the sum of exponentials, you're very hamstrung mathematically, you know, because you can't, like, take the log of both sides, you know, and it's like, wow, you know, so I don't really want to, I don't know, actually, you could take the log of the, you could take e to the minus t over tau 1, make that your x variable or something like that. But in any case, you can get to these A1 and A2 variables either linearly or non-linearly. And then basically what they do is they develop this chi2, which is A2 over A1 plus A2. And then they make chi2, they're sort of substituting that for this holding parameter. Right? And so they just plot chi2 versus time after the heating pulse. And then, you know, it looks like like that.
Dr.
You know?
Terrell, can you move down a little bit? Thank you.
So there's a jump, and then there's a slower approach. And most of the information, most of the kinetics, is on which they base their arguments is from this second part here. You know, so there's a quick jump and then a slow approach. And this is complete in about 200 microseconds. So let's so what we can do is we can go back and we can answer some of the questions, the remaining questions in the text. There's some stuff about guanidine and these other so-called steady state measurements. So what is meant by steady state? Well, you can just say equilibrium might be better, but steady state is not absolutely correct. It's simply the persistent structure at a given temperature. You know, after 200 microseconds or more at temperature. Okay, so this next one, I don't know. I might have known at some point in the past when I made up this question, but I'm not really sure now. I know that folded is one extreme. Folded proteins have native function, right? Denatured do not. Random coil, I don't know. And molten globule, I'm not sure. Harley, do you have any insight into what the molten globule might be?
Well, usually the molten globule, when you have the energy landscape diagram for protein folding, it's kind of like midway in the funnel.
Mm.
And random coil is just, that's what they call an sort of like an unfolded structure where it's not like an alpha helix or a beta sheet, and it has its own like kind of profile as well.
Got it. And then the molten globule is intermediate structure in the folding process, right? Oh God, the significance of this graph. This is, this provides the long time endpoints for the, that the kinetic experiments approach. And reach, right? Okay. So supercooling, that's easy. That's simply cool to below the freezing point, not indefinitely stable. But it will denature this protein reversibly. Okay, so the initial temperature as a substantial unfolded fraction this is 1/n of the folding spectrum for this experiment. This is -6 Celsius plus 5e9 Celsius per second times about 4e, oops, minus 9 seconds equals 5 or 21c. Wait, no, that'd be 19, right? Because -6 plus 25 is 19c.
For some reason, I thought the starting temperature was -4.
Okay. I'm not being super picky about this. Okay. Okay. This is about as poor a wording as you could possibly get. So the methionine 131 contacts tryptophan 14 upon folding, and this causes tryptophan 14 to quench. That long lifetime component quenches. Okay. You know what? I don't want to do that one. Let's draw a timing diagram. Timing diagram is easy. And it's important, right? So let's go here. And the timing diagram, I think we already did it, right? There's the left and the right, a heating pulse. So this is the Raman has shifted YAG laser. So this is the 1500 nanometer that heats. And this is off for the remainder of the experiment. Then there is a every 15 nanoseconds, there's a very short this is the UV laser, 240 nanometers. Now, if I were to plot the temperature versus time, temperature versus time is going to start at -4 degrees, and then it's going to shoot up and up again to about +21 degrees. That's going to be constant. And then there's going to be the PMT signal, which is going to be going like that. And then what we're going to do is we're going to analyze tau 1, tau 2, A1 and A2. Tau 1, tau 2, A1, A2, etc. For each of these time windows, each of these decays, and then we're going to plot A2 over A1 plus A2 versus time. And then that's going to go there's a very fast part. And a 200 microsecond rise. In this latter part, is the approach of tryptophan to methionine.
Dr. Terrell, can you please move the paper up a little bit? Thank you.
Yes. That kind of cuts the heart out of the paper, I think. More or less all the important creature comforts are there. And I totally didn't get these lined up properly. But I hope you can sort of interpolate what I mean here. So, anyway, what we're going to go on to talk about here is Mossbauer spectroscopy. Just because it's fun and cool. And I'm going to describe an experiment that links all kinds of quantum mechanics. Heisenberg, uncertainty principle, recoil, less emission, nuclear overlap of S wave functions, S electrons, and relativistic processes involving photons. Photons in gravitational fields. So you don't have to write any of that down. I was just writing it there because some people were still copying the last thing. But I'm excited to get into Mossbauer briefly. But I'm not going to bore you with it yet. I'll save that for next time. I have all these notes for it. Right? Nah, you can get to talk about any of them. But I'm still bogged down in this paper. I hate it. But I made the question shorter. I eliminated that one part. So so now you guys know what to write.
Dr. Terrell,
Yes.
is Mossbauer spectroscopy, do they use that in space? Why is gravity in this?
I didn't quite hear the question. Is Mossbauer spectroscopy?
Do they use it in astrophysics or what? Why is there photons and gravity?
It's used for a lot of weird stuff, you know. There's like 10 or 12 different elements where you can see a Mossbauer effect. And the most important one is iron. And iron 57, you can measure the magnetic fields and the like the s orbital populations and other stuff about the configuration, the orientational, or the I think the coordinated environment of the iron centers in oh, you know what else we can talk about? We can talk about XAFs. So we'll talk about Mossbauer and XAFs, and that'll wind up this semester. But Mossbauer is just really weird. It's a resonant emission absorption process for gamma rays which come from the nucleus. There's just a really interesting blurb where cobalt 57 undergoes electron capture and transforms into an excited state iron 57 nucleus, right? So it undergoes an electron capture and immediately shoots at an X-ray, right? And then 100 nanoseconds later or thereabouts, you get there's actually 3 gamma rays that come out, but you only use one of them. And it's this 14 keV gamma ray. It's a low energy gamma ray from different nuclear spin states, right? And this nuclear gamma ray can come out of the nucleus with 0 recoil. It just depends on the crystal that it's coming out of. If you have a well-ordered crystal of iron 57, then, or cobalt 57 rather, then the iron radiation can come out with no recoil. And if there's no recoil, and the lifetime of the state is 100 nanoseconds, then the energy width of the gamma ray that comes out is extremely narrow. And it's like 1 part in 10 to the 11th of the energy of the gamma ray. So you can tune the energy of iron 57 sources relative to absorber by Doppler shifting. You can Doppler shift them just a few millimeters per second. And the absorption will go up and down. And it is so amazing. Plus, you can do all kinds of other interesting stuff with it. We'll talk more about that next time. All right. Are you guys bored? Good, I've done my job.
I'm hungry.
All right. Excellent. Well, go have some food and enjoy your weekend. And I will see you all next Tuesday, but not next Thursday because I'm going to be having Turkey Day. Okay, we'll go find your dad.